Today we're going to talk about some Riemann sums and some definite integrals. Now, when you read your learning target, it says we're going to use definite integral notation and some geometry formulas to find the area under the curve. So it's a continuation of what we've done using the rectangles back on Thursday and Friday, to the trapezoids on Monday, and now Riemann sums. I know it says remember Riemann sums. Oops. Sorry, is the process of finding the sum of the area under the estimated curve, and the rectangles may be split, equal lengths, or unequal lengths. Here is the difference with Riemann sums. You can split them equally or not equally. You'll hear me always say that I will usually try to split them evenly because it makes the math a little bit easier. So the more rectangles, the more to estimate area accurately if they're real sharp or real small. So you might be able to have a rectangle here, but then it might have to be a little tighter as you go along. So that's where Riemann sums come in handy, where you might be able to go here and here and here and help yourself figure some things out. Now, the one thing that is different about Riemann sums is, I don't know why that's not let, there it goes. If you have your XY axis on here and you have some kind of a curve, usually Riemann sums are called Riemann sum left or Riemann sum right. So I'm going into making my rectangle tool. And when you make a rectangle, notice that this rectangle that I built was based off of the left side or here. So that would be considered a Riemann left. This would be a left. Ooh, I don't have the pen on. This would be considered a left. Sorry about the color changes. And then if I were to draw a rectangle, and I freehanded this one instead of using the shape. Sorry. If I use this one, this would be considered a Riemann right, because do you see how the right side is touching the function? So that's the only difference between Riemann sums, is they go left and right or middle, and that's the same as the types that we have used. So again, the more rectangles you use, the better, and the actual area of this is considered the limit of the sums. So now into more important applications. I've been saying that this is an integral. Now we're going to actually see how this integral is going to work. A definite integral has a little a down here or a number here and a number here, and this is going to be telling us the range at where we want to find the integral from a to b. So when I see this and it says set up the definite integral for the area, first of all, it's telling me do not evaluate. We'll get to the exact evaluating in a second. When they want us to set it up, step one, we need to draw a picture. And I was bad on my notes because I did not give you an XY axis, but don't worry, I'll remember that when it comes time for a test. So I'm drawing my XY axis right there. Second thing that you need to be able to do when you're drawing this is actually draw the function itself. So I'm going to change colors. You need to be able to figure out what these shapes look like. Well, hopefully you can figure out that this is a line, and this line has a y-intercept at 4, and then it comes down to over 1 and down to over 1, and you could draw a line, and this would be, let me switch colors, this would be the region that you would want to find the area of. Okay, so that's step one, draw the picture. Step two is going to be write the integral. So now we're going to actually start to write the calculus stuff that goes along with this. So as I'm writing the integral, I need my funky little s. On the bottom of the S is the left point that you're checking. I am checking 0, so 0 is on the bottom. The right point is going to be the top number, so I'm going from 0 to 2. I write the function 4 minus 2x, and I'm going to put a little dx behind it, and that is my integral. And eventually we're going to learn how to do this algebraically, but for right now we're just trying to get the pictures and giving you a way to solve this thing. Okay, so now let's go to problem number 2. From problem number 2, notice it's from -1 to +1. So as I draw my xy axis here, I gave myself x and y on each side. I'm going to draw my integral. Now, I know that you guys probably don't know what that looks like off the top of your head. You could use your calculator if you need it to, but you should know some of these, and these were supposed to be equally up and down. And -1 falls right about here, and +1 would fall right about here. And what I would want to do is I would want to find the area in between those two. So I would want to find the area of all of this. Okay, but step 2 is only writing the integral for it. So my integral is going from -1, that's the left point, to +1, the top point, or the right point, all over 1 over x squared plus 1. And I have to put that dx behind it because it's an integral, and that's what it's stating. So now we're starting to make the calculus tie. So on to the back side. Now that we have some of these kind of weirder shapes, let's take a look at trying to find the exact area under the curve. So first thing that I'm going to do, it says sketch it. So in red, I am going to sketch this, and the function is 4. It is only a horizontal line. So at 1, 2, 3, 4, ooh, that's supposed to be a horizontal line. I'm looking at this, ooh, let's extend this line. I was bad when I drew this out. From -3 to +3 is the area that they would want me to find. So if I block this off at -3 and I block this off at +3, this is the area that I want to find. You should be able to identify what kind of shape it is. It is a rectangle. Now, since it's a rectangle, it's a shape we know how to solve. Can you find the area of a rectangle? I hope you can. We've been using them. It is just base times height. So my base is 6 units. My height is 4 units. So this exact answer would be 24. And that would be square units if I would say that we were in centimeters, inches, feet, whatever. Okay, so now let's take a look at the next one. The next one is a line. You should be able to identify that the line has a y-intercept of 5 and it's a downward slope. So 1, 2, 3, 4, here's 5. Here's my dot. And if I come down 1 over 1 at 1, 2, 3, 4, 5, there's the next one. And it's going to look, oops, kind of like a triangle. It wants me to find my integral from 0 to 5. So I am finding the area of the triangle here. So area of a triangle equals 1/2 base times height. So it's going to be 1/2. My base is 5 units long. My height is 5 units high. So my area turns out to be 25 halves, which is the same as 12.5. And again, that's units squared. There we go. Finally, last example. Maybe you don't know what this looks like. Hopefully you can see. Let's go over 1, 2, and 1, 2. I'm trying to space this out. I know what this shape is. If I didn't know what the shape was, I could put it on my calculator, and it is a semicircle. It wants us to find from -2 to +2, and notice this would go 2 units up. If I put 0 in here for x, do you see that would be the square root of 4, which is 2. That's how I knew when x was 0, y was 2. Okay, so area of a circle is pi r squared. This is not a circle. This is an area of a semicircle. So the area of a semicircle means that I'm going to take pi r squared, but take half of it. Okay, so figure out what you know. My area is going to equal pi. Hopefully you can see your radius is, oops, let me get the eraser. Your radius is 2. Don't want to write over it so you guys can see it. And then you're going to square it, and then you're going to divide this by 2. This turns out to be 4 pi divided by 2, which turns out to be 2 pi. And again, that would be units squared. So you just found the area of that semicircle. As I said, today, not a lot of new stuff, just put into some new formation and learning how it's going to tie into the calculus. Do your homework tonight. Tomorrow we will review, and on Thursday you will be taking your mid-chapter test. Be good.